Welcome! Today, we'll explore an interesting problem titled Keyboard Row. This challenge tests our ability to analyze constraints related to QWERTY keyboard rows and form solutions around them. Let's dive into the problem and uncover the solution together. In this problem, we are given an array of strings called words. Each string in this array is made up of English letters, which can be either uppercase or lowercase. Our task is to identify and return a new list of words from this input array where every letter in the word can be typed using only one row of a standard QWERTY keyboard. To clarify, the rows of a QWERTY keyboard are divided as follows. Row 1 contains the letters QWERTY, row 2 includes asterisk, and row 3 consists of ZXCVB and M. It's important to note that this is a case-insensitive problem, meaning uppercase and lowercase letters are treated as equivalent. The input constraints specify that the array can have up to 20 words, and each word can have a maximum length of 100 characters. Furthermore, all characters in the words are guaranteed to be valid English letters. The output for this problem is a list of strings derived from the input array. Each word in this output list must satisfy the condition that all its letters belong to only one row of the QWERTY keyboard. To illustrate this, let's consider an example. If the input array is words equals hello, Alaska, dad, peace, the output should be Alaska, dad. Here's why. The word hello contains letters from row 1, such as E and O, as well as row 2, including H and L, so it doesn't qualify. Alaska, on the other hand, has all its letters in row 2, so it is valid. Similarly, dad is valid because all its letters belong to row 2. However, peace is invalid because it uses letters from both row 1 and row 2. This example highlights how we evaluate each word against the keyboard rows. Now let's explore another example. If the input array is words equals OMG, try, the output will be try. Breaking it down, the word OMG contains letters from multiple rows. O and M are in row 1, while G belongs to row 2. This disqualifies OMG from the output. Meanwhile, try qualifies, as all its letters T, R, and Y are part of row 1. For a third example, consider words equals type. The output in this case is an empty list, because the word type uses letters from both row 1, such as T and Y, and row 2, specifically P. Since no word in this input array satisfies the condition of using only one keyboard row, the result is an empty list. To summarize, the word type fails because it includes letters from multiple rows of the keyboard. Now let's discuss some constraints and edge cases for this problem. First, the input array words can have anywhere between 1 and 20 words, and each word can have a length between 1 and 100 characters. All words are guaranteed to contain only English letters, and uppercase and lowercase letters are treated as the same, meaning the solution needs to handle case insensitivity. Some edge cases to consider include an empty input array, which should produce an empty output list. Single-letter words, such as O or Z, will always satisfy the condition since they inherently belong to a single row. Additionally, if all words in the input array fail to meet the requirement, the output should be an empty list as well. Mixed-case words, like QWERTY, must be properly evaluated by converting to lowercase or handling case insensitivity during processing. These considerations ensure the solution is robust and handles all possible scenarios correctly. To solve this problem, we first need to understand its constraints. Each word in the input must be formed using letters from only one of the 3 rows on a QWERTY keyboard. These rows are the top row, containing letters like Q, W, and E, the middle row, including letters like A, S, and D, and the bottom row, which has letters like Z, X, and C. Since the input array of words may include both uppercase and lowercase letters, it's important to normalize them to a single case, such as lowercase, to ensure consistency during the comparison process. Ultimately, the problem reduces to checking whether all the letters in a word belong to a single row, which forms the foundation for our solution strategies. One approach to solving this problem is a brute force method where we iteratively check each word against the rows. For this, we represent the 3 rows as sets of characters. Then, for each word, we determine which row the first letter belongs to and check if all other letters in the word are from the same row. If they are, we include that word in the result. While this approach is simple to implement, it can be inefficient when working with large inputs since it involves repeatedly checking each character against the rows. To address this inefficiency, we can use an optimized approach. By pre-computing a dictionary that maps each character to its corresponding row, we can streamline the process. For instance, we assign letters like Q and W to row 1, A and S to row 2, and so on. Then, for each word, we use this dictionary to quickly determine the row of each letter and verify if all letters map to the same row. This approach reduces redundant checks and improves performance. The time complexity for both the brute force and optimized approaches is O, n*m, where n is the number of words and m is the average length of each word. However, the optimized approach pre-computes the character-to-row mapping, which takes constant time, and uses this mapping to efficiently validate rows. Space complexity remains minimal, requiring only O1 additional space for the dictionary. The main advantage of the optimized approach is that it eliminates redundant character checks, simplifying the validation process. Another alternative is to use regular expressions for row validation. Here, we create patterns for each row, such as $QWERTY plus $, for the top row, and check if a word matches any of these patterns. While this method is concise, it can be slower due to the overhead of regex pattern compilation and matching. Additionally, regex may feel less intuitive compared to other methods, making it harder to understand and debug. The strategy we chose for solving this problem is the optimized approach with pre-computed character-to-row mapping. This method is both efficient and intuitive, avoiding the overhead of regex matching and the inefficiencies of the brute force method. By leveraging a dictionary for quick lookups, it ensures that row validation is fast and avoids unnecessary checks. Comparing the three approaches, the brute force method is simple but repetitive, while the regex-based solution is concise yet less efficient and harder to grasp. The optimized approach strikes the best balance between clarity, speed, and simplicity, making it the most suitable choice for this problem. This ensures a solution that is not only effective but also easy to implement and understand. In this problem, we need to determine which words from a given list can be formed entirely using letters from a single row of a QWERTY keyboard. The keyboard is divided into 3 rows, the top row containing letters like QWERTY, the middle row with *, and the bottom row with ZXCVB and M. To solve this, the first step is to pre-process the keyboard rows by defining them as sets of characters. Using sets is efficient because it allows for fast membership checks on average in O1 time. For simplicity and consistency, all the sets and input words should be converted to lowercase to handle case insensitivity. This pre-processing step sets the foundation for the algorithm. To determine which words are valid, we start by initializing an empty list called valid_words where we will store words that can be formed using a single keyboard row. We then iterate through each word in the input list, checking which row its letters belong to. For each word, we convert its letters into a set of unique characters and check if this set is a subset of any one of the 3 predefined keyboard row sets. If the word's letters belong entirely to one row, we add the word to the valid_words list. For example, if the word's unique characters form a set that is a subset of the top row, middle row, or bottom row, it qualifies as valid. At the end of this process, we will have a list of words that meet the criteria. One of the key insights of this algorithm is the use of set operations for efficiency. Representing the keyboard rows and the word's characters as sets allows us to perform subset checks, which are both expressive and computationally efficient. For each word, the subset operation runs in OK, where K is the length of the word. This is much faster than checking each character individually. Additionally, pre-processing the input by converting all rows and words to lowercase simplifies case insensitivity handling and avoids repeated conversions during the iteration. It's also important to consider edge cases. For example, if the input list is empty, the algorithm naturally returns an empty list. Words with non-alphabetic characters can either be ignored or validated separately, depending on the problem's constraints. Mixed-case words are automatically handled through the lowercase conversion, ensuring correctness. The algorithm uses 2 primary data structures. First, sets are used for the keyboard rows because they enable fast membership checking and subset operations, making them ideal for this problem. The space complexity for these sets is O1, as their size remains constant regardless of input. Second, a dynamic list is used to collect valid words as we iterate through the input. This list grows dynamically with the number of valid words, so its space complexity is O(m), where m is the number of valid words. Analyzing the time complexity, let n be the number of words in the input and k the average length of each word. Converting each word to a set takes O, k, and the subset check for each word also takes O, k. Since we process all words, the overall time complexity is O, n asterisk k. For space, the predefined sets take O, 1, while the temporary set for each word takes O, k. The result list requires O, m, space, so the overall space complexity is O, n plus k, assuming the input is stored in memory. The Python implementation of the algorithm begins by defining the keyboard rows as sets. These sets are stored in a list for easy access during the subset checks. The find_words function takes a list of words as input and processes each word one by one. For each word, it converts the word to lowercase and then into a set of unique characters. Using a generator expression, it checks if this set is a subset of any of the three keyboard row sets. If the condition is met, the word is added to the valid_words list. After processing all words, the function returns the valid_words list. For example, given the input, hello, Alaska, dad, peace, the function identifies Alaska and dad as valid words because their letters come entirely from one row. The output in this case would be Alaska, dad. To understand the behavior of the algorithm in different scenarios, let's look at some edge case examples. For an empty input list, such as, the output is also an empty list because there are no words to process. If the input contains words like QWERTY, ASDF, ZXCV, they are all valid because each word's letters belong to a single keyboard row, and case insensitivity ensures proper handling. On the other hand, words like hello, peace, result in an empty output because their letters span multiple rows, making them invalid according to the problem's rules. These examples highlight how the algorithm correctly handles various inputs while adhering to the constraints of the problem. This solution is designed to solve the problem of determining which words in a given list can be typed using only one row of a QWERTY keyboard. Explanation. 1. Keyboard rows as sets. We first define the three keyboard rows, top, middle, bottom, as sets of characters. The use of sets allows us to quickly check if all characters in a word belong to a specific row. 2. Normalization. Each word is converted to lowercase to make the comparison case insensitive. This ensures that uppercase letters in the input won't cause mismatches. 3. Subset check. For each word, the solution converts it into a set of its unique characters and checks if this set is a subset of any of the keyboard row sets. If it is, the word can be typed using only one row, and it is added to the result list. For output, finally, the list of valid words is returned. This approach is efficient and handles edge cases, such as words with mixed case, empty input, or words containing characters from multiple rows. The code is concise and focuses on correctness and clarity. Here, we begin by defining the three rows of the keyboard as sets for quick membership testing. Each set corresponds to one row of the QWERTY keyboard. The top row includes characters like Q, W, E, and so on. Similarly, the middle row contains letters like at ESD, while the bottom row includes Z, X, C, and others. Using sets allows us to effectively check whether a word can be formed using only the characters of a specific row. Next, we initialize an empty list called result to store the valid words. The method then iterates over the input array of words. For each word, we first convert it to lowercase to ensure case-insensitive comparison. After that, we create a set of characters from the word, which helps us quickly determine the rows it uses. Finally, we check if all the characters of the word belong to one of the keyboard rows. If they do, the word is added to the result list. Here, we start with the top row check using the contains all method. If the word doesn't fit entirely within the top row, we move on to check the middle row. Similarly, if the word matches all characters in the middle row, it gets added to the result list. Finally, for words that don't belong to either the top or the middle row, we check against the bottom row. If the bottom row contains all the characters of the word, it is added to the result list as well. After processing all the words in the input array, we convert the result list to an array using the toArray method and return it as the output. This ensures that the final result is an array of strings, consistent with the method's return type. This implementation is both efficient and easy to understand, leveraging the power of sets to perform quick membership checks and simplify the logic for row validation. In this problem, the objective is to determine which words from a given list can be typed using only one row of an American QWERTY keyboard. The keyboard is divided into 3 rows: the top row, containing letters QWERTY, the middle row, with *, and the bottom row, containing ZXCVB&M. The input words are case-insensitive, meaning we treat uppercase and lowercase letters equivalently. For the output, we return a list of words that meet the condition of being typable from a single row. For instance, if we take the input list of words, hello, Alaska, dad, peace, the solution begins by defining these keyboard rows as sets for efficient membership testing. We initialize an empty list called result to store the words that meet the criteria. This sets up our solution for processing each word in the input list to check which row, if any, contains all its letters. We now begin processing the words in the input list one by one. Starting with the word hello, we normalize it to lowercase, resulting in hello, and then convert it into a set, which gives us the unique characters H, E, L, O. Next, we check whether all these characters belong to any single keyboard row. First, we check the top row, and the subset test returns false. Then we check the middle row, which also returns false. Finally, we check the bottom row, and again, the result is false. Since hello does not meet the condition, it is not added to the result list. Moving to the next word, Alaska, we normalize it to Alaska and convert it to a set, yielding a, L, S, K. Checking the rows, the top row test returns false, but the middle row test returns true, meaning all letters of Alaska are in the middle row. Therefore, Alaska is added to the result list, which now contains Alaska. Continuing with the word dad, we normalize it to lowercase, resulting in dad, and convert it into a set, which gives us D, A. We then check whether this set is a subset of each row. The top row test returns false, but when we test the middle row, it returns true, meaning all the letters in dad belong to the middle row. As a result, we add dad to our result list, which now becomes Alaska, dad. The next word is peace, which we normalize to peace and convert into the set P, C, E, A. Checking the rows, we find that this set is not a subset of the top row, the middle row, or the bottom row. Since peace does not meet the condition, it is not added to the result list. At the end of this process, our result list contains Alaska, dad, which is the output for this example. In the second example, we process the input list, OMG, try, row. As before, we define the keyboard rows and initialize an empty result list. Starting with the word OMG, we normalize it to lowercase, OMG, and convert it into the set, OMG. Checking the rows, we find that this set is not a subset of the top row, the middle row, or the bottom row. Therefore, OMG is not added to the result list. The solution continues with the next word. For the word try, we normalize it to lowercase, resulting in try, and convert it into the set, T, R, Y. When we check row membership, we find that this set is a subset of the top row, meaning all the letters in try can be typed using the top row. As a result, we add try to the result list, which now contains try. The next word is row, which we normalize to row and convert into the set, R, O, W. Checking the rows, we find that this set is also a subset of the top row. Therefore, we add row to the result list, which becomes try, row. The final output for this example is the list, try, row. This problem's solution highlights a few key insights. By using sets, we can efficiently check whether the letters of a word belong to a specific keyboard row. Normalizing the words to lowercase ensures that the solution is case-insensitive, treating uppercase and lowercase letters equivalently. Additionally, by performing subset checks for each row, we ensure that only words whose letters are entirely contained within a single row are included in the output. These techniques combine to create a solution that is both elegant and efficient. To analyze the time complexity of our solution, we start with the initialization of the keyboard row sets. Here, we are creating 3 sets, one for the top row, one for the middle row, and one for the bottom row of the keyboard. This involves iterating over the characters in the strings QWERTY, *, and ZXCVB&M. Since these strings have constant lengths 10, 9, and 7 characters respectively, the time required to initialize each set is constant. Therefore, the overall time complexity of this step is O1. Next, we process each word in the input list. Let's say there are n words in the list, and the average length of each word is m. For every word, we perform three main operations. First, we convert the word to lowercase, which takes m time. Then, we convert the lowercase word into a set of unique characters, which also takes m time. Finally, we check whether this set is a subset of one of the keyboard row sets. Since the size of each keyboard row set is constant, this operation also takes m time. Adding these up, the total time complexity for processing one word is m plus m, which simplifies to m. Now, since these operations are performed for each of the n words in the list, the total time complexity for processing all words becomes n*m. This gives us the overall time complexity of the solution, which is n*m. Turning to space complexity, let's analyze the components. First, the keyboard row sets top_row, middle_row, and bottom_row are initialized once and require constant space. Each set holds at most 10 characters, so together they contribute 1 space. Next, we consider the result list, which stores the words that meet the criteria. In the worst case, all n words from the input list could be added to this result list, and since each word takes m space, this list would require n*m space in the worst case. Finally, for each word, we temporarily create a lowercase version and a set representation. Both of these require m space, but since they are temporary and replaced for each word, they do not contribute to the overall space complexity. Thus, the total space complexity of the solution is n*m, primarily due to the space required for the result list in the worst case. Comparing this approach to a brute force method, the naive approach would involve checking each letter of every word against all three rows of the keyboard. This means iterating over each character of every word and comparing it to 10 characters in each row. For n words and m characters per word, this results in a time complexity of n*m*3 by 10, which simplifies to n*m. While the brute force and the given solution have the same asymptotic time complexity, the current solution is more efficient in practice due to the use of set operations for fast subset checks, which reduce constant factors. For space complexity, the given solution also avoids explicitly iterating through all keyboard characters for every word, utilizing constant space sets instead. Both approaches, however, share the same n*m space complexity in the worst case, as it is dominated by the storage of the result list. When tackling this problem, there are several common mistakes to watch out for. First, ignoring case sensitivity can lead to errors since uppercase and lowercase letters, like Q and Q, belong to the same keyboard row. To avoid this, always normalize your input by converting all letters to lowercase. Another frequent issue arises from incorrect row definitions. Forgetting to include letters like M in the bottom row can cause failures in edge cases, so double-check your row setups. Additionally, some solutions incorrectly check if only some letters of a word belong to the same row, instead of ensuring that all letters do. This violates the problem's requirements. Efficiency is another consideration. Using nested loops for membership checks can be costly, with a time complexity of n*m. Instead, opt for sets to achieve 1 membership checks. Finally, don't overlook edge cases like empty input or words without characters, as these can cause runtime errors. Always validate your input thoroughly. Now, let's focus on insights that are particularly helpful in an interview setting. Efficiency is key. Interviewers expect you to optimize your solution by using data structures like sets for fast membership checks, rather than relying on brute force methods. Be mindful of edge cases, such as handling words with mixed case letters, empty lists, or single letter words, as these are often tested. Recognizing patterns in string manipulation problems is also crucial. For example, many such problems require normalization, like converting strings to lowercase, and leveraging efficient data structures like sets or dictionaries. Lastly, in interviews, it's important to articulate your approach clearly. Discuss the trade-offs between different methods, such as why you might choose sets over lists in this case, to demonstrate your thought process and understanding. This problem is part of a broader category of string manipulation and validation tasks, and there are related problems that you might find useful for practice. For instance, LeetCode 953, verifying an alien dictionary, involves validating words based on custom rules, which is conceptually similar to checking for keyboard row consistency. Another example is LeetCode 929, unique email addresses, which emphasizes string normalization and manipulation, much like this problem. Of course, the original problem, LeetCode 500, is a direct application of these concepts. Additionally, LeetCode 49, group anagrams, is another string-based problem that focuses on pattern recognition and grouping, making it a valuable exercise for honing your skills in this area. There are multiple approaches to solving this problem, each with its own trade-offs. The brute force approach involves checking each character of each word against the 3 keyboard rows using nested loops. While this method is straightforward to implement, it's inefficient, with a time complexity of n*m, and becomes impractical for large inputs. A better option is the set-based approach, where you use sets for each row and check if all characters of a word belong to one set. This still has a time complexity of n*m, but it's faster in practice due to the membership checks provided by sets. The trade-off here is the extra space required for the sets. Another efficient method is the hash map approach, where you map each letter to its respective row and verify if all characters of a word belong to the same row using the map. This approach has similar time complexity to the set-based method but uses less space. However, it's slightly more complex to implement, so you'll need to weigh the benefits of efficiency against simplicity based on the context. Great job! Today, we tackled the keyboard row problem and explored efficient ways to process strings based on constraints. Remember, practice makes perfect, so keep solving similar problems. Don't forget to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!